Hey, we're back. All right. Thanks for coming, checking in again. You're kind of doing some binge watching here of science, while you're at home. So anyway, hey, today we're going to be talking about Mr. Newton and his first law, basically. In honor of that, I wore my Science Rock shirt. There's Isaac himself rocking out. So wearing the wig and everything. But let's first talk just a little bit about Mr. Newton. He lived in England a long time ago. These are the dates that he was born and passed away. Roughly 300 years ago. Every idea that he came up with is 3 centuries old at least, and we're still using them today and still talking about him. He's obviously one of the big top dogs of science, one of the great minds that has ever lived. We're lucky to have that there. So besides Newton's laws, he's famous for his laws of gravity, which you have just studied last week. You've already studied optics, that light is really many colors. He was doing studies on that a long time ago. Some of you might go to high school or college and take a class called calculus. You can blame Mr. Newton for inventing that. So, did a lot of amazing things in his life. I was just reminding myself, though, it's kind of interesting that he did come up with his gravity ideas, apparently, while he was away back home on the farm. His family had a farm, and he left the university from the city there because there was a plague going around Europe, and it was in England at the time. So he was practicing his social distancing by heading home and sitting on the farm. Apparently, whether the apple actually hit him in the head and that helped him figure out what gravity was or not, that might just be a story, but it's kind of interesting that we're studying Newton in our little time of a pandemic here. So one cool job he had later, I just have to mention this, after he kind of retired from science, he became the director of the Royal Mint there in England. Pretty cool, huh? And it's not making candy like you might think. It's even better than that. It's making money. Yeah. His job was to track down the counterfeiters that were a really problem back then. And he was really good at it. He put a lot in jail, even put a few, on the hangman's noose there. So if you are bored over the break, or not the break, but bored while you're spending time at home and you need something to read, I might suggest a biography of Mr. Newton. Pretty fascinating things that he did there. So before we jump into the laws of, I want to look at your front page of your notes where it says important ideas. There's 3 things about what Newton's laws are all about that I'm going to talk about here really quick. First one is the idea that, hey, it's nice to know all these rules and these laws, but just having this knowledge, whatever, doesn't do you a lot of good. If you remember what I talked to you in my class at least about, hey, what's the power behind science? The power is, exactly, to be able to predict. It's right there in your notes and underlined. You might circle that a few times there. So, and it's amazing what we can do. These 300-year-old ideas are now helping people put rockets into space, and they orbit the Earth. They leave Earth's orbit and they go and they rendezvous with Mars as it's circling the sun. They can orbit around Mars and then send another little probe down to land safely and on the surface of Mars and move around. It's just, mind-boggling that how good these laws are working and the fact that we're still using them. I was watching a show the other day about an internal combustion engine and all the moving parts inside and the forces that are on, like the piston rod, and how that has to survive, millions of ups and downs as it works there in the engine there. And they were talking about using Newton's laws to figure this all out. So incredibly predictable. I could share a quick story about my younger life. I think I might have been 3rd or 4th grade, and I was, for some reason, I was on the roof of my grandpa's barn. He was a farmer, and I was hanging out on the edge of the roof there, and I was actually doing some predicting of myself. And how much force would I have to apply to my body so I could go horizontally through the air and land in the middle of the stock tank that was there. The stock tank was full of water, for the animals there, and that would have been a nice soft landing. But I didn't do the math right or whatever, or maybe I, miscalculated something there. But I kind of landed on the edge of the stock tank, and which is made out of metal, not the landing that I wanted there. But I was only 3rd grade, hadn't studied Newton's laws yet, so you'll have to give me a break there. What's it say next on your notes? Newton's laws are universal. This is awesome. Pretty much everywhere, everything in the universe, boom, Newton's laws. Easiest question you're ever going to get, all right? in your life. And you'll get a question like this week is, hey, give me an example of Newton's laws. Boom, me, standing still right here, Newton's laws. You nailed it. Your fingers typing out the answer to an example of Newton's laws. Ah, there you go, Newton's laws. An apple falling on somebody's heads. You guessed it. The moon orbiting the earth. Newton's laws. The tides that come in and out because of that. Newton's laws. So you playing catch in the backyard or dropping a ball or whatever. You know, all of those things. So it's not going to be a challenge whatsoever for you to come up with an example of Newton's laws. So just a little heads up here. When you answer questions on a worksheet and specifically on the assessments, it's going to say, like it kind of says on your notes here, if you look on the second page of your notes, it's going to ask you for a good example of Newton's first law, for example. Good being there's certain things that lend themselves better to explain what Newton's first law might say. And then it says to explain it. So you've got to throw in the science words behind it. You got to tell me what that means, basically. You can't just say, you know, me driving in a car. Well, you got it, Newton's laws. But use the terms, explain what's going on. What does the first law, for example, specifically say about that? So make sure you understand that, and I'm going to try to give you plenty of examples of good examples, if you will, for this unit here. So, hey, the final thing about Newton's law is that there's many ways to explain them, many ways to state what they say. I've given you actually in your notes 2 ways for each of the 3 laws. If you go online and you look them up, I'll guarantee you'll see different ways to do it. If you go into textbooks, you're going to see even more different ways. Lots of ways to do it correctly. If you come up with your own way of saying it and it's correct, awesome. That's great. That would be perfect for you to do. But you don't have to do that. You can use the terms I give you. If you like something you read online better, you're more than welcome to use that. If it's correct, it's correct, okay? There are a few details that you need to get in there that we're going to talk about here, so let's make sure you understand that so we can be, boom, right enough, correct? All right, so, all right, let's get into Newton's first law. Are you ready? Newton's first law. That's a terrible name, don't you think? Newton's first law. So we're going to give it some names. Other people have given them the same names. So your notes tell you that Newton's first law is this I word. Let's all say it together. 1, 2, 3. I didn't hear you guys. All right. 1, 2, 3. You got it. Inertia. Woo! Yay, inertia. Your job is to try to say inertia correctly in a sentence, at least a couple of times before this week's over. Okay? Try to look for examples of this. Any Bill Nye fans out there? Science guy, right? His opening theme song, what does it say inertia is? Inertia is a property of matter. Yes. Well, and that's not wrong. It's not really right. There's a lot of properties of matter. It'd be nice if you added a few more details to that. So, but anyway, I'm not here to criticize Mr. Nye or his song at all. But so inertia. Let's sum it up with this idea: that resist change. I don't want to change. Okay. That could be my attitude or my motto as I get older in life here. I don't want to change, right? I'm good enough. Probably really just lazy. I don't feel like changing. But now I'm not talking about, my attitude or my weight or something like that. This is Newton's law, so we're talking about objects moving. Objects don't want to change their motion, basically, okay? That's pretty much what that's saying, okay? But wait a minute, are objects changing their motion all the time? Well, yes, they are. All right. So obviously, what do you got to do to make something change? If it doesn't want to, well, you got to force it. You have to literally apply a force. All right. So that word you learned back in week 1 when you're talking about forces and net forces, there we are again. So basically, anything a push or a pull, one object on another, lots of different forces in this universe. Let's start to think that way. Okay. So hang on here. Let me try to get my thoughts together. All right, so let me show you this. I've got an example here for you. Let me show you my assistant. So, been spending a lot of time by myself here in science class. This is my new best friend. His name is Wilson. Say hi to the kids, Wilson. Hey, kids, how you doing? All right, so, hey, Wilson is retired from the tennis courts. He's no longer getting beat around by tennis players. He's here to help us learn a little bit of science. So, what if we put old Wilson right here in the middle of our table and see if Newton's laws applied to him? 1, 2, 3. Do your thing, Wilson. Check it out. What are you noticing? Is Wilson resisting a change in his motion? Yes. What would we have to do to get Wilson to change his motion? We'd have to apply a force to him. Okay. Wait a minute. You guys see what I'm seeing here? Isn't there a force being applied to Mr. Wilson right now? Do you see it? Exactly. It's the table. The table's pushing up on Mr. Wilson here. Let me replace the table with my hand so I can kind of tell you what I'm feeling here. So I feel, my hand is pushing up on the tennis ball just a little bit, not too much, all right? But that's okay because the tennis ball is pushing right back down. So there are forces acting on the tennis ball, on Wilson here, but he's not changing his motion. So what's going on? We need to add something to our law about this idea of balanced and unbalanced forces. Balanced means they're equal. So right now, the forces are balanced and I've got no change in motion. If I wanted to get Wilson to move, I'd have to push up harder than he's pushing down on me. So here we go. I'm going to try my best. And there it goes. Ta-da! Amazing, the things you can see on videos these days. All right. So, so I unbalanced the force. I pushed up harder, and guess what? Wilson moved. Okay. So let's see that again, and notice there's a lot of stuff going on here. Let's pick out some more details here. So, what the heck? All right. So while I was pushing up on him, the forces were unbalanced. But the moment I let go, am I pushing up on him anymore? The answer is no. All right. So what Newton would say is happening is, hey, now I'm going to resist change in motion. I'm just going to keep going in this direction at this speed, forever. And obviously that doesn't happen. Matter of fact, the moment I let go, he starts to slow down. All right. And eventually he slows down to a stop, and then he speeds back up and comes right back down to me there. So there's got to be something else going on here. And you guessed it. It's been around forever. It's something you studied last week. We're talking gravity here. So we got to add another idea besides unbalanced and balanced forces here. We got to add the idea that there's some outside forces, gravity being one, that are always here on the surface of the earth and constantly changing the motion of objects here. So matter of fact, gravity is what's pushing Wilson down into my hand, and it's what's requiring me to put a force back up on that. Okay, I then unbalance that force. As soon as I let go, my force is gone, but gravity's relentless. Gravity's everywhere all the time. It's slowing him down, stopping him, speeding him up, and bringing him right back down to my hand. So, a little trick you got there, Wilson. So, we're going to have to change our law to make it a little bit more detailed. It's not objects just don't want to change their motion, or objects don't want to change their motion unless you apply a force to them. It has to be objects won't change their motion unless you apply, and here it is, unbalanced and outside force to them. All right. So basically, that can sum up pretty much everything you're going to see here on the surface of the earth. So gravity is one of those unbalanced forces. The other one, of course, is what else you studied last week? Friction, exactly. So if I give Wilson a little shove sideways, once again, I unbalance the force with my hand, I push him sideways, but the moment my hand lets go, he's on his own, all right? He doesn't keep going and going and going and going. He eventually stops, not necessarily because of gravity, but in this case because of the friction, primarily between him and the table there, all right? So what do you think? Let's go ahead and read what it says there on Newton's first law. Objects do not want to change their motion unless an outside/unbalanced force act on them. Voila. And the two big giant outside forces here on the surface of the earth, gravity and friction. All right. So, let me talk about this before I forget. To get rid of gravity and friction, you can get rid of friction by just leaving the Earth's atmosphere. That means you have to go quite a few miles up in space in a space capsule or a space suit. All right. And technically, you can get to where there's basically no friction. To get outside of the Earth's gravity, you really have to go a long way away from Earth to get it down to where it's close enough to zero that you can ignore it. There are astronauts on some videos that I'm going to show you here and that you can look up a little bit later that are looking like they're in zero gravity, but they're really close to Earth. They're doing something called free fall while they're in orbit. And if you want some extra credit, I'm going to throw this at you here. Hey, you can look up this idea of a vomit comet. All right, look up some videos on that, see what that's all about. It used to be just for the military, but now you can actually pay some money and you can go up in an airplane. It's an airplane, by the way, and you can experience no gravity for a little bit here, without having to go tens of thousands of miles away from the Earth out into space. So anyway, hey, got a few more quick demonstrations of Newton's first law to show you here. Wilson's been practicing this trick a lot. He's very excited to show it to you. So all right, so I'm going to take a string here. I don't know if you can see the string that I've got, and I've got a little piece of the handyman secret weapon here on the back, a little piece of duct tape. I'm going to attach that to Mr. Wilson there. All right, you ready, buddy? Yeah, okay. So, and we're going to get him going in a circle. Woohoo! Are you feeling it? Yeah, I'm feeling it. All right. So, hey, objects do not like going in a circle, all right? Even though the speed is constant, excuse me, the direction is continually changing, all right? This is constant acceleration as you go in a circle. You're changing your direction every moment around there. It's going to require a force to do that, and that force is what the string is all about. What if the string was to break, or the tape was to come undone, or I was to let go? What would be Wilson's direction then? And woo! Ah! Come here, Wilson. Ooh, that was work. I worked that out perfectly. He's safe. He's good. All right. But if you were paying attention, the second I let it go, his speed didn't change and his direction stopped changing, and he went off in a straight line. Of course, gravity curved him down a little bit. Friction from the wall bounced him back and forth. All kinds of things are happening there. But there you go. So objects do not like going in a circle. That requires a constant force because it's constant acceleration. One other quick example here. This little guy it looks like a little soccer ball, but it's more in a disc shape, and it has an electric fan on the bottom here. I'll turn it on. And you can probably hear it running. It's going to blow air out the bottom this direction, right? So if I set it on the table, there's air between the disc and the table, and that greatly reduces the friction between the table and it, and it's free to kind of move around. I don't know if you've ever seen hovercrafts or something like that, but it's basically the same idea. If I was to turn it off, wait for it to stop, and try to do the same thing, not nearly as much fun. Friction, boo. Although friction good sometimes, actually. So we live with gravity and friction constantly. We're never, unless we go into space, right? Or unless we're free falling for a few moments here now and then. Maybe once a little bit on ice or something, you can experience very little friction, but we never experience zero gravity and zero friction on the surface of the Earth, and we kind of forget that they are always a part of what we're seeing here. That's sort of the genius of what Newton came up with 300 years ago, was that he could see through all that. He could see that, hey, objects really want to just keep doing what they're doing. If you could get rid of gravity and friction, they're going to go on a constant velocity in a straight line forever and ever and ever until another unbalanced outside force acts on them. So one thing I think I forgot to mention really fast from on the back side of the second page of your notes is why do we love amusement parks so much? And why is the playground so much fun? All right? How fast are you going at the amusement park there? What's the fastest roller coaster go? Somebody should look that up for me. I don't think I bet it's under 100 miles an hour, all right? It's really not too much faster than you ever drive in a car. So if you really just want speed, perhaps you've been on a commercial airliner before, and when you're up at cruising altitude and cruising speed, you're going over 500 miles an hour. And how did that feel? Think about that. You're going on a constant velocity in a straight line. Your elevation isn't changing. You're not accelerating at all. And what do you feel? Pretty much nothing, all right? You could even take a nap on that airplane ride if you wanted to. You could hear the sounds, and there's a few bumpings once in a while, but as long as everything's going right and safe, man, you're going over 500 miles an hour and you don't even feel it. So what's the deal with the amusement parks? What's the deal with the merry-go-round there at the playground? What is the deal? Exactly. You are constantly changing your motion. You're changing speed and or direction almost all the time, all right? And that's what you feel. Think about it, all right? Change in motion requires a force, all right? And you feel forces there. So constant velocity does not require a force. There's no net force on that, basically. You're just You're just sitting there in the airplane flying along it. You know, you could be, you know, the astronauts up in space, when you look at those videos, they're doing 17,000 miles an hour or faster. And they don't, you know, they're not going to feel it. It's, you know, they're not accelerating, basically, is what I'm saying. So, anyway, there you go. Newton's first law. I'm going to call it on this, and then we're going to come back and do the second and the third law all together in the next video. Thanks for watching.